Right, hello everyone. This is Ardasher Nasrudinov with my finished machine learning final project. So this project's goal is basically to create a depth estimation algorithm. Basically, we have some 2D images, and we want the computer to learn to map depth based on those two images. And for that, obviously, an ML model would be the right choice. So that's why I implemented it, and I used nonlinear regression. Though usually this would be a computer vision problem or like a classification problem. I thought that nonlinear regression kind of fitted pretty well with the whole kind of heat map or depth map, and is something we learned in class. So that's what I implemented. Um, and then the main point of how I implemented this would be that I try to use as little from PyTorch or like existing libraries as I could. I mean, I still implemented stuff like backpropagation with PyTorch just because it's some complicated math and error prone, and there wouldn't be much of a learning experience if even if I hard coded it. But a lot of the other stuff I did hard code, as we'll see later on. So just to quickly go over the data pipeline, the loading logic is pretty standard. It's just going to show you some examples of the images, then the solution sets of how far everything is, or like the depth map from NYU. Then the data pre-processing logic is also fairly standard. I mean, and NYU's data set was pretty large, so I had to use the extract. Like I had to create a function to extract patches. What I ended up doing to optimize was so I don't have to load like millions of tiny patches into my hard drive. What this code does is it takes the full image, sends it to the RAM, and then extracts patches from there, so the GPU is busy, and doesn't create a huge bottleneck with like millions of patches just hanging out in my hard drive. So next would be the model architecture. I run that. Okay. So again, the kind of point here is that I tried to implement as much as I could by manually. It's a fully connected neural network is what I implemented here, and the input size. I guess that's important. I should have mentioned that in the data preprocessing. It's the patches are 5 by 5 pixels, and there's 3 color channels, so that's 75 features each. Right, and then, so I mean, I guess the layer 1, it takes these 75 units and it expands them to 128, and then it compresses them to 64, then 32, and then obviously the output layer is just 1 unit. I guess batch normalization here is important as well. Oh, I mean, I should say this creates like a kind of funnel shape, and yeah, that's kind of important, I guess. And batch normalization is also pretty standard here. I don't know what to say about it. Yeah, it's also implemented, like hard code implemented. So as well as the forward pass, I actually do the dot product and stuff manually instead of just using PyTorch. I will say, obviously, so there are existing models like the UNet, and if I use some convolutions as well, probably I would have gotten better results. But the point was to kind of understand the back end of this stuff and use what we learned in class. So this is what I ended up going with, the fully connected neural network. So I guess finally it's just the training loop. I've got about a minute left. So the important part here is that I hard coded the Atom optimizer, and which I guess I chose over just like simple linear regression because it maps better to like it will learn from the weights individually, and so it just maps better to the kind of task at hand. And I'm running out of time, so yeah, as you can see, the training loss, this is just a random sample. The training loss is pretty good. It's on a downward slope, but you can see that with just this short demo, there's like 5 epochs and like maybe like 16 images analyzed. So the precision isn't too good, but you can tell it's still figuring out that these features are separate from these features. So like these are the shirts, and so it's not great with this little training, but it still does a good job, and it works. So thank you very much for listening.